The framework of hypothesis testing is very widely used, and it's quite important. In fact, oftentimes when people are thinking about statistics as it's applied to scientific inquiry, for instance, they're often thinking about hypothesis testing as sort of the pillar stone of statistics in that realm. Now, despite its importance or despite its wide use, it's not without its critiques, it's not without its critics, and as a result, it's sort of worth understanding why are some people very critical of the framework of hypothesis testing, where do these criticisms lead, and are there any ways to still make use out of hypothesis tests in spite of these criticisms, or to at least integrate the criticisms into how we go about thinking about hypothesis testing or using hypothesis tests in practice. So while hypothesis testing can be a very powerful tool, there are going to be many valid critiques of the framework. We'll look at a few of them here today. There are more of these. These can also be laid out in more depth, but it's worth at least thinking through what some of these criticisms are. So the first critique is this idea that everything in practice is actually significant. So sort of very often we're going to be testing the null hypothesis that some parameter is equal to 0, right? We're going to be trying to code the idea that there is no effect, that the medical treatment did not do anything, that one process is the same as another process, right? This is sort of what we're going to be coding as the null hypothesis. However, in practice, there's almost nothing that is going to have an effect of 0, right? If you think about introducing some sort of medicine, it's very unlikely that that's actually going to have a 0 effect. Maybe it harms people a little bit, maybe it helps them a little bit, maybe it doesn't have a big effect, right? But almost certainly it has some effect. The reason that you're testing this medicine to see if it's doing anything is because you have some biological basis for thinking that the medicine is going to do something. And so it's very, very unlikely that there's actually going to be absolutely no effect of treatment in this case, right? And if we know that it's very unlikely for there to be an effect of 0, we might ask, well, why are we testing the null hypothesis that this effect is actually equal to 0, right? So no matter what, we're always going to see some effect, might be very small, but it's almost certainly not 0. And so if no one is going to be believing this null hypothesis, why are we even testing it? And so instead of actually testing the null hypothesis that the statistic equals 0, that the parameter equals 0, rather, we might instead consider different effect sizes or other measures of how different from 0 it really is, right? Because perhaps it's a non-zero effect, but it's just so small that we don't care about it. It's not practically significant, right? And so alongside reporting, did you have a statistically significant result or not? It's also important to report, well, what was the actual effect size that you're seeing? And you should be doing this whether you find it to be statistically significant or not. If you don't find it to be statistically significant, you're probably going to go on believing that the effect is 0. But it is worth reporting, well, what did you actually observe? How much uncertainty was there? And by reporting all of these other quantities, we're going to have a much better picture than if you say the effect was equal to 0. Because we know the effect is probably not actually equal to 0, it just might not be different enough from 0 for us to actually care about it. The second critique that we'll look at is the prioritization of p-values. So in the framework of hypothesis testing, p-values are really prioritized above everything else. Even if we're using critical values, still at the heart of that, there's really a p-value that we're just not calculating. So at the core of them, a p-value is just a statistic. It's something that we're computing given some amount of data. And the statistic is going to be measuring the level of evidence that we have against the null hypothesis, right? So lower values of lower p-values correspond to stronger evidence against the null hypothesis. So this is going to be a continuous measurement, right? And then what we do is we take that continuous measurement, we look only at it, and we say, it's either statistically significant or it's not. So we have this measure of how much evidence is there against the null hypothesis, and then we make a yes, no, a 1-0, a binary decision about this. In this process, we're losing information when we discretize the p-value here. The other thing that we're doing is ignoring plenty of other important factors, right? And so we lose information because, for instance, if you observe a p-value of 0.06, right, and you're testing at the level of 0.05, well, then you say it is not statistically significant. We fail to reject the null hypothesis. Right? But we would have drawn the same conclusion if we had a p-value of 0.20 or of 0.50, right? And so in all of these cases, we have very different evidence, but we ultimately report the same thing from it. Okay? And so this sort of is a strange place to be. But on top of that, we're also ignoring the rest of the context that has gone into calculating this p-value. So, for instance, we don't consider what prior information do we have, right? So what did we know about this result before we ran our hypothesis test? We don't include the scientific plausibility of any of the hypotheses that we're making. We don't include any measures of the quality of the study or the quality of our data. We also don't really include the practical significance of the result. Right? There's all sorts of pieces of information that we might want to include that we're not including when we're thinking about p-values. And so the critique of hypothesis testing here is that the p-value, it's a useful measure itself, but we should probably report the p-value rather than a level of significance, right? Whether it's significant or not, rather. We should report the p-value because that contains lots of information in itself. But then we should also think about how are we measuring or how are we talking about the rest of these quantities and everything else that might matter to us in our study. Okay, so there are things that are important beyond p-values, and hypothesis testing can oftentimes prioritize p-values above everything else. And so we want to be cautious about that. The third critique here is that the null hypothesis is actually a straw man argument. Okay. So very often we're going to be in cases where the null hypothesis is really not believable. And so we know that we should be selecting the null hypothesis to be conservative and to be our default belief about the state of the world, but often we're selecting it as a convenient hypothesis in order to refute. Okay. So if we're selecting a straw man null hypothesis, we're selecting one that is not plausible itself. When people talk about straw man arguments, what they're referring to is an argument that no one really believes, but you pretend like that's what people believe so that you can easily argue against it. So with our straw man null hypothesis, what we're doing is we're picking a null hypothesis that no one really believes, but it's going to be easy to refute with our data. And as soon as you've refuted the null hypothesis, you have a statistically significant result. And as soon as you have a statistically significant result, then you've done real science, right? And so here, if we're not choosing good null hypotheses, if we're not choosing null hypotheses that people actually believe, well then anything that we're concluding here is not going to be particularly relevant, right? Because if we don't believe the null hypothesis, then what have we learned by refuting it? If we say, started from a place that we didn't believe this, and then our data tell us, oh, well, we shouldn't believe that, what have we actually learned? And the answer is nothing, right? If we falsify something that we already believe to be false, did we learn anything? And the answer is no, because that's where we are already at. And so here, we really need to be making sure that the null hypotheses that we're choosing are valid null hypotheses in the sense that they are conservative, they are what people actually believe about the world, right? And they don't reflect a straw man version of this. We shouldn't just test, is this thing equal to 0, because that's what other people are doing, right? If we set up an actually strong null hypothesis, one that people would actually believe without evidence, and then we're able to refute that, well, now we've actually learned something. Right? And so we need to be really careful in the choice of our null hypothesis here. The final critique that we'll look at is that it's an easy framework to abuse, right? Null hypothesis significance testing is easy to abuse. And so why is this the case? Well, the number of decisions that need to be made by the researcher in the hypothesis testing framework makes it easy to abuse. Because there's often going to be many justifiable options for any choice that the researcher needs to make. And given that in the null hypothesis significance testing framework, there's one specific goal to get to, this is a really concerning tendency, right? Because the goal that we're getting to is to find a statistically significant result. That's really the only thing that we care about once we start significance testing. And so because of that, because we have just this one goal, and because there are so many choices that we need to make, researchers are free to make choices that will help them achieve this goal, even if those aren't the correct choices to make. But it can be hard looking from the outside to know, was this actually done? Because maybe their choices seem justifiable in some sense. Okay, so Intentionally or not, researchers might perform p-hacking. With p-hacking, what we're thinking about is choices that are being made or decisions or parts of the analyses that are being done that are going to artificially deflate the p-value, which is going to let researchers find statistically significant results where they really shouldn't have. And so because of this, it becomes a really difficult framework to work within if you're trying to be honest about the science that you're doing. So some ways that people might p-hack, intentionally or not. If you're considering one-tailed alternatives, then you're able to effectively cut your p-value in half just by changing what your alternative hypothesis is. You might select unbelievable null hypotheses, right? If you select a null hypothesis that's not believable, then you're going to end up with a larger effect size that's going to give you a smaller p-value. Oftentimes, people are going to throw away what they would call outliers in the data, right? So if you have a data point and it's an inconvenient data point, perhaps you just delete that from your records and you say, well, it was an outlier, it didn't fit the pattern, right? So if you start deleting data, well, then you're potentially going to be p-hacking. You might also perform many different analyses, but then only report the ones that were significant, right? So you test a whole bunch of hypotheses about a whole bunch of different data, and then you're just reporting what happens to be significant. This is also going to be p-hacking, where if you're not reporting everything that you've done, then there's sort of not this clear path through your analysis. Okay, and so all of these different choices, there might be reasons why you're making them, right? But regardless of that, they open up the door to results that aren't really significant or shouldn't be significant, but have been found to be significant because of the researcher behavior. And this is very easy to do within the framework of hypothesis testing. It happens a whole lot, and it's something that we really need to be careful for. So whenever you're thinking about making a decision in the hypothesis framework or hypothesis testing framework, you should be thinking about, well, what is the justification here? Is this for scientific inquiry? Do I have sort of the context or the subject matter to back up the choices that I'm making? And if not, you should reconsider all of those choices that you are making. Okay, so much of scientific inquiry is going to rest on the hypothesis testing framework. However, it's not without its flaws. And so what we need to do if we're going to be doing hypothesis testing, and if you're going into science, it's going to be something that will come up. You need to be careful about your application of this framework. You need to be responsible and transparent, right? The choices that you make, the decisions that you're using actually have to be justified, they have to be communicated, and they should be supported by this goal of seeking the truth rather than this goal of achieving statistical significance. You should consider what else is important beyond p-values. You should report those things. You should report how did you do your analyses, why did you make the choices that you did, and if ever you find yourself making choices to try to find that statistically significant result, then you should reconsider that, because that's not a good way for getting to the truth. And working within this framework of hypothesis testing, it's going to make that very tempting to do. And because of that, there are many people who think we should be moving away from hypothesis testing. For now, it's an important part of statistical inference, and it's worth knowing this as a skill. But as you go on to apply it, please be careful in the application of everything within this framework, because it is sort of this place that is a very sticky situation to be in.